Yeah, so because most of you do not know this school, so I just use 5 minutes to talk about this school. All right, so we are in Northern California. So all right, so we are in Northern California, 2 hours away from San Francisco and 2 hours away from Silicon Valley. And the school is really in the middle of nowhere, you can see. And so it's pretty new, and we are next to, well, 1 hour away from Yosemite National Park. And so these are some of the places you can go. If you come visit us, you can come to Yosemite National Park and other, there's a few other national parks. Oh, which one do I go? Okay, so we are also close to Lake Tahoe. If you go to NIPS, then in the next few years, it will be held in, well, actually last year it was held in Lake Tahoe too. It's about 3-4 hour drive from Merced. The reason they said
it's a long drive.
Yes, because of the mountain. Actually, it still takes 4 hours from Silicon Valley to drive up to Lake Tahoe for ski. And we are also close to some, we are close to Sierra Nevada, where there are a lot of mountains. So there are a lot of stuff that you can see over there. And we are also about 3 hours away from the Pacific Ocean. And there are a lot of national parks too, Monterey Bay and stuff like that. And the school was set up in 2005, and it was one of the newest UC campus. And I went there in 2008. And by far, this is a very small campus if you compare with all the other. There is UCSF. You probably do not know this one. This is medical school. Aside from that, we are very, very small. And we have about, well, right now it's about 6,000 students, and it's very small. We only have a few buildings there. And we have 3 schools, engineering, science, and SHA. And let's see. All right, so we have several typical programs in any other schools. And in ECS, it's very small. We have 8 faculty members, and we have 25 students. I think it's smaller than the Mubarak's group. You can hold fit in our program. And we have people in different areas, AI, computer vision, graphics, so on and so forth. It's really small. Yeah, so some other pictures. This good day. And then the snow is very important in California, because you probably do not know that there's a canal that ships all the water from Northern Cal to Southern Cal. A lot of water from Los Angeles came from Sierra Nevada. And so in the wintertime, it's very important to measure the number of snow we have, because that would affect a lot of agriculture and the water consumption in Southern Cal. Oops, I think that's all. Yeah, and then, okay, so today I'm going to talk about some recent work on tracking. Especially I would talk about 2 work on, okay, 2 recent work that we use sparse representation for online tracking. So this is a bit different from what you are doing here. Yeah, this is a bit different from what you are doing, because I know here you deal with multiple objects, and then you deal with very challenging conditions. Here I talk about single object, but the main difference is that it's online tracking. All you have to do is just enclose the object of interest in the first frame, and it does its thing automatically. And most of the time it runs in real time. So that's the main difference. Okay, so this work is done with a student in China and his advisor. Okay, so, well, as you know, you wrote quite a few survey papers on this, so at least one. So when you look at tracking algorithms, there are many ways to categorize them. Okay, so you can categorize them in terms of generative approach or discriminative approach, and you can also categorize them in terms of global or local features. And so you can see there are several words that use different things, and then so the question is.
Should the second option keep the current constant?
Sorry. No, it's okay. Don't worry. So the question.
I think in order for him to capture your video, maybe stay.
Oh, I see. Okay, good. All right, so the main thing is that there are several ways to put things together. And recently there are several works on that. For example, there's one that uses L1 tracking. Well, it's called L1 tracking. Basically, you use simple, well, no, I should not say simple. You use sparse representation to capture appearance of objects in terms of temperature. And it is one of the first few works that use sparse representation, inspired by.
From Maryland?
No, it's, well, he graduated from Maryland,
yeah.
And he was a student of David Jacob, but he's now at Temporal. So the idea is pretty simple, but it is based on EMA's face recognition work. So the thing is, if you have temperate, then you can represent the object in terms of temperature, and then you add in several trivial temperatures such that you can account for occlusion. And the problem with this works pretty well, but the problem is that it does not. It handles occlusion reasonably well, but it's very time-consuming. Although there is new work that they speed up the process. The thing is, because they use a particle filter, so you draw a lot of particle filter. If you draw, say, 600 particles, then you will solve 600 L1 minimization problem. So that's kind of slow. And the other thing, they use global templates for that. Oops. Let's see. How do I? Okay. And there are several other works that try to improve on top of that. Okay. One use discriminative approach. The one that I mentioned is generative approach. Basically, how do you track objects? Well, you sample around the current target, and then you try to find one with minimal reconstruction error, and that will be your target. And there are, of course, if you have generative approach, then you will have a discriminative approach. So the other work that try to separate foreground from background. But they put all the temperatures into one large set of temperatures. They do not differentiate positive or negative temperatures. And later on, this group from Rodgers, they also use similar approach, but they change back to generative approach. But then they change from the global template to local templates. And they do that, and they got some quite decent results. So the idea in this work is very simple. So basically the idea is just to combine discriminative approach with generative approach, and you put two things together. Basically, take the best part of both worlds and try to see, each one has its own merit, so you try to put them together and see how it works. And that's why we call it collaborative tracking. Okay, so the main idea is this. Okay, so if you look at generative approach, if you account for appearance by reconstruction error, then the thing is, if you take a foreground patch, okay, or you sample around a target, and if you separate temperatures into positive temperate and negative temperatures, then suppose that you extract one patch near a target, then the foreground patches can be better represented by foreground temperatures. This is very intuitive, right? And on the other hand, background patches will be better represented by background patches. It's very straightforward. If you choose the other way around, then basically you still can reconstruct that, and then with a small error, but then the error will be larger. The other thing is that also you would use more coefficients to do that. For example, if you have a foreground patch and you use a negative temperature to reconstruct that, you still can do that, but the coefficient would not be sparse. Okay? So by looking at a sparse coefficient, you can tell a lot of things. All right, so the idea is this. So you have so basically instead of using one big chunk of temperatures, one big set of temperatures, we separate positive and negative temperatures. So for this object here, this one, okay. So for this object here, and suppose that we know this is a foreground object. Then if you use positive temperature to reconstruct that, then you will have a smaller error. And if you take this guy and use negative temperature to reconstruct that, usually you will have larger errors, and the coefficient would not be as sparse as the other way around. That's the main motivation. So basically, what you can do is that, okay, the same thing here. For one patch, then you solve two optimization problems. So you send it to positive temperature and negative temperature, because you don't know which one's which. And then you look at the reconstruction error. And that will tell you this guy, the sample patch will be most likely from positive or negative set. And that's how you determine that. All right, so then the reconstruction error should tell you that. Basically, you have one reconstruction error from positive set and the other one from negative set. And that will tell you which one is which.
A prime is what?
I'm sorry?
A prime.
Okay, this is a set of positive templates. Basically, you only have, from one target location, you can sample a little bit, and so that you have a set of templates. And so, likewise, for negative example, you can sample around. I mean, basically, for this guy here, you can sample around the target, but with a little bit overlap is fine, but within a radius. And then as long as you know that there is no positive template, a positive target, then you can consider that as negative templates. And you put this together.
These are bases, right?
What's that?
These are bases for your sparsity.
They are like bases. These are your bases.
Yes, bases. Yes, these are bases.
And how do you select those?
Well, you just sample around a little bit. Yeah, and then also from previous frame. We will up because it's always about online tracking. So at one frame you can sample spatially, and for the next frame you can keep a few from a previous frame.
So in that equation, one time you set A prime to A plus, and then you look at the reconstruction error.
Yes.
And then you set it to A minus and look at the reconstruction error.
That arrow will tell you which one is which. Basically, from this, if this guy, this will tell you the confidence. Basically, if this arrow is small, then basically this confidence will be high. Okay, and the other way around.
Right, I'm just trying to understand the relation between A prime and A plus and A minus.
Yes.
So A prime is sometimes set to A plus, and
yes, of course, okay. So what happened for online tracking is that you know the current object location. How do you track? So you sample around this object. So you draw a lot of samples. Some of them, if you draw a sample enough, in the next frame you will find one right on the target. But most of the time, you would not be right on the target, right?
Right.
So that's the main thing. Okay, the other thing is that if you look at sparsity, then you can also use that for feature selection. And this is not a way to do that because of dimensionality reduction. I won't go into detail, but basically this is not a way. If you put this capital A that consists of both A plus and A minus, you put them together and you look through all the vector elements, then you will be able to find out the elements that appear most in both sets. Therefore, you can also do dimensionality reduction by exploiting sparsity. All right. And that's that. And then afterward, you just update. And this update model is pretty simple. Basically, you just keep a field from the current frame and you discard the oldest one, and that's about it.
So when you know the position in the current frame, you go to the next frame, around that current frame in the next frame, you sample different windows, and for each window you try to express that as a positive and negative, right? In terms of your sparse.
Right.
And you find whichever is the best, and you say
yes. Yes. That's it. Yeah. So this is one. Remember, this is collaborative model. So this is one using holistic or global templates.
Okay.
Yeah.
Mm-hmm. So in this thing, the intuition is like, one is that you are maintaining these bases which are in the way the
yes.
Source,
yes.
Right?
Yes.
But you are also
right. Right, and you also exploit the sparsity. Because, for example, if you look at PCA or all kind of stuff, for any object, you can always use any trivial template to reconstruct it. There are no. It's just that you need to use more bases. You need to use a lot of coefficients to do that. And if this guy is really right from the positive one, then the coefficient number of coefficients will be smaller.
So right now you don't have the trivial template.
We do. We just sample. We do. We just sample around that. Because if you know in the first frame, you know where a target object is, and you just sample a little bit around that, then you can get a set of negative templates. In fact, it's very easy to get a lot of negative templates. It's just that whether some of them are good or bad, because anything outside the target region can be considered as negative templates.
But how about the positive? In the first frame, you only have one target.
Yes. So then you sample. You just perturb a little bit. In the first one, you can perturb a little bit. That will still help. Yeah. Good question. Yeah, that's all right. In the beginning, you always need a little bit trick for that. in all kind of online tracking algorithms. Okay, so this is the one with global or holistic templates. Okay, and the other one is that we use discriminative approach. Okay, so this is the discriminative approach. Okay, basically because from reconstruction error you will be able to tell which is which. Okay. And the other one that we do is to use local representation. So this is generative approach. So what happens is that instead of using global template, you can divide the whole parts into several small local parts, patches. Okay, and then from this you can think this way. You can also do vector quantization, or you can do any kind of clustering, and then some of the patches will be similar, and you can use those spaces to represent this object, and that will tell you whether the object is occluded or not. So instead of using global one, you can use local patches for that. So that's the idea here. Because if you look at faces or an object, you always share some local similarity. Okay? And then if you look at over time domain, then basically you can tell whether the object is occluded or not. I think some of you are doing parts-based tracking, so that's a similar idea. Okay, so then, like I said, so basically for each one, then if you do first you do vector k-means, and then you can cross it and find some basis, and then for each one of them, you can use the basis, the dictionary, to represent that, and you can get a set of sparse coefficients. And from the sparse coefficient, you can also tell whether a part is occluded or not. That is the same idea. Basically, and then for all the parts, you can just build a histogram based on all the coefficients. And from the coefficient, you can tell whether our object is occluded or not. This is, like I said, so basically temporally you can see whether the construction error is large or not. Because if you look at the same position and the object is occluded, then it's very different from what you have seen before. So if you use the same basis to reconstruct that, the error must be higher, and the coefficient will be not as sparse as the other way around. That allows you to tell whether the object is occluded or not, a part is occluded or not. And from that, you can say that is important because for online tracking, you always need to update appearance. How do you know that whether the object is occluded or not? From this, you will be able to tell a little bit. Otherwise, if you use global template, if you just simply use global template, if a part is occluded, you will take this part as foreground. But if you use this local representation, then you will be able to figure out whether one region is occluded or not. And if you can find out that, then you can discard that part when you update the model. Yes?
How robust for rotational invariance?
It handles a little bit. Okay, so in terms of tracking, there are several ways to model the motion. Okay, so here we only use similarity transform. We only use three parameters, x, y, and the scale. If you rotate, it still can handle that. It's just that the rectangle will not rotate. Okay, that's another way to do that. Okay, but because of local representation, you can still account for whether within the rectangle, some parts are from the foreground object or some parts are from background objects. You still can handle that. I'll show you some results. Yeah, but in terms of tracking, there are all kinds of variations. You are right. Okay, I'll show you some results later. Okay, so so like I said, so basically from that you will be able, and for matching, basically you just use histogram to compare. After you find out which part is occluded or not, and then you can use histogram to compare. Again, you still sample, like the previous one, you sample around the target region, and then this time when you compare objects, or when you compare a sample to a model, basically you just compare them based on histograms. That's all. Okay, so the update is still very simple. This is similar to the discriminative generative, the first part, the discriminative holistic part. And yeah, so basically the good thing about this local representation is that you can use this to account for appearance change caused by occlusion. Okay, so I'll show you something. Now, you have two models. How do you combine them together? Well, obviously, there are many ways to fuse all the results together. The easiest way is just multiply them together. You have one score from the discriminative holistic representation, and the other one is local generative approach. And both of them will give you some confidence where the object should be. And then you put two scores together. And if you can find one location where both scores are high, then that's where you want to put your object is.
So you need both of these?
Yes.
Right?
I also have a result to show both either one of them. Yes. But I don't have it here. In a journal version, we have that. Yes. We do have it.
And what's the intuition? Like, why do you need both? Like,
well, so the first one, basically, the first one, if you just simply use global temporal, then it's not easy to handle occlusion. Yeah. Even though it's L1 minimization, even with that, you can handle that, but it does not handle as well as local patches. So that's why. Ideally, we want to use discriminative local representation. But before we do that, we just do discriminative holistic representation.
But I mean, can you just use the local? Forget about the
Oh yeah, we can do that, but it's just that for local, basically, you put all the things together unless you do dimensionality. Otherwise, it's not as robust as discriminative approach. Whenever you, like I said, the ideal case would be local discriminative. That would be the best approach. But before we figure out a way to do that, basically, we choose two things together. And I don't know whether local discriminative will work better or not. I don't know. But I would think it should be a good way to go. If you look at all the tracking results, most of the time, discriminative approach tend to give you better results. Question?
Yeah, so for the local generative model, the patches or like the local features, they come together in a compositional function, right? So
yeah.
There is no room for any deformability, or is there?
No, there is, because it is sequential compare. It's not like a fixed template. If you have some variation, it's still fine. Plus, you have a lot of patches. Yeah, I'll show you some results. And at the end of this talk, I will show you some benchmarks. Okay, so these are some. Okay, so all the codes and the data are available on my sites, so you can take a look at those results. I will compare with MILTracker that we know, and some of them are built by us. And
is that a tracker?
No, we didn't have this one.
But he has another one tracker, right?
I don't know which one. No, but we didn't use that one.
No, there's one tracker by him.
well, so this meal is done by us, and then this IVT was done by us.
We use IVT.
Yeah, so we use quite a bit. And then there are pro and con for each one of them. I can go into detail with you. But
which RBT is yours?
IVT is ours, and meal is also ours. Yes, both. And
so this new one is better than RBT? Or?
Yeah, I can show you 31. I mean, because if it's not better than that, at least in some cases, So I now show you with more result on how to compare with all the tracker. And this one is a very challenging sequence. And oops. All right, this one you know for sure. You work on surveillance, and this one. Apparently, I didn't copy the file over, okay? But you are more than welcome to just Google my name and then find my webpage. You can find all the results and the data set and the code. And there are some other, yeah, I didn't copy all the video over, but that's, wow. And some numerical results, I don't expect you to read all the detail now, but you can, later on you can take a look at that. Yes?
I have a question. I want to know what is the motion model you have used in this?
For this one,
yes.
It's very simple, just X1 and scaling.
And how was the sampling in the next frame?
Oh, sampling, well, you just sample spatially, right, and then scaling. Yeah, yeah.
Gaussian or just uniform?
Simple Gaussian, just random walk, very simple one. Yeah, we didn't use.
So, like in one of the sequences, you showed that the human was walking behind another person.
Yeah.
I want to know the reason that you were able to handle the occlusion was the motion model you used, or it was because of the local.
It's because of I believe it's because of representation.
Okay.
Yeah, but I have to look into that and then let you know exactly what's going on. But if you ask me now, I would say it's because of representation. Because the sampling part is very simple. And likewise, we have different ways to evaluate that. These are two standard ways to do that. Yes?
So the bases are updated in some
Yes,
way?
yes. Yeah, we always, this is all about online tracking. Today I'm going to talk, I mainly focus on online tracking. Basically, in the first frame, you localize the object you want to track, and afterward you just need to use that and update the model, and hopefully you can track as long as you can. Okay, so what else? Okay, so because I need to present 2 other things, so I may skip some details. But if you have more questions, send me emails or just look up the paper. Okay. And so the idea is very simple. This work is based on a collaboration of 2 trackers. One is based on discriminative, holistic, or discriminative global model for that, and with local generative model. So based on these 2 trackers, then we will be able to handle all tracking much better. And actually, it works pretty well. And we have another work that compared with survey tracker, it performed very well. And I'll show you in a bit. Yes?
What's the reason you cannot do the local discriminative model?
I'm not saying you cannot. I just say I haven't figured out yet. I don't say you cannot. Okay?
Maybe this for new student, you can explain briefly what you mean by generative.
Oh, generative basically means like, okay, you have a one representation, right? You have appearance. Okay, either you can think that as a vector. And how do you write in terms of linear combination of the bases? Such that if you take a square root, if you take an Euclidean distance between these 2, the error is small. Like for example, if you have 100, or let's just say 99, this number is represented by what? 9 times 10 plus 9, right? And if you have 2 bases, then you can use 9 times 10 plus 9 times 1. If you have only one basis, what will it be? It will be 9 times 10, right? So the error is larger. So the question is, how do you find all the bases such that the number of coefficients will be small? And that is how you do with for tracking. For one appearance vector, and you find all the bases such that you can represent very well.
So that's the discriminative.
This is generative. Because yeah, discriminative basically you have a foreground background. Usually for discriminative, for tracking many, you have 2 classes at least, foreground, background, and then basically for one you just sample around. From current location you draw another sample, and they will tell you, okay, this sample belongs to foreground or background. And beyond that, it also gives you some confidence. If it's very similar to, how similar is that sample how similar is that the sample to the model that you have?
But
So
this terminology is not universal, right?
it's not
That you have some kind of distribution and you can
correct. So right. So if you talk to machine learning people that generated that basically they will think that it's mostly about probabilistic formulation. But in PCA or stuff like basic generative, it just means that you can, from one model, you can generate that appearance. Our model can do that. From all the basis, you can generate one appearance like that. For discriminative approach, even if you have model, you will not be able to regenerate the appearance.
But in local one, are you also able to do this?
Yes.
These pieces and you have bases.
Yes.
And so on,
Yes.
right?
You can use bases and put them together and then reconstruct an image that is very similar to the one that you see.
And also the global one, you are able to do the same thing.
We can, yeah, but the thing, you are right. But the thing is that we use both arrows, and then the arrow will tell you. That's why we call it discriminative.
Okay.
Yeah.
In the language of dictionaries and sparse coding, what you call generative, is it the same as reconstructive?
Usually, yes. I would say yes. It's just reconstruction. Yes, generative. When you have that, yes.
Just curious. So your basis is uniform random distribution. Is that how you're choosing your basis?
No. Well, there are several ways to do that. Okay. For global one, basically, in the first one you just perturb a little bit, because if you see this one is basis, if you strip a little bit, just a little bit, or rotate a little bit, that will still will be a good basis. For local one, basically based on k-mean clustering. You divide the whole patch into several smaller ones. Among all of them, some of them will be similar. You don't need all of them to represent that. You just need a small set of that, and then use that to account for appearance.
And then how do you estimate the sparsity?
How do I estimate? Well, basically that's that is controlled by one regularization term, one known term. That helps a lot. That's the main difference between the conventional L2 regularization and L1 regularization. And L1 turns out well, you can go into a theory, you can go into a lot of theory with that, but basically if you use with L1, it turns out that the result will be more sparse.
How do you know how do you estimate what this sparsity would be? How do you estimate lambda basically?
We don't necessarily need to care how sparse it is, as long as it's sparse enough. I mean.
Oh, okay. So the resolution.
Yeah, we don't care whether it is the sparsest representation we can find or not, as long as it's good. Okay. All right. So this is one word that we use sparse representation to do that, and there are several ways, and you can tell that there are several ways to do all this kind of stuff. And this is another work done with a student in Hong Kong Polytech. And this one is basically in recent years you can tell that there are a lot of works on sparse representation and compressive sensing. So this one gives you some flavor about how you can use similar idea from compressive sensing for tracking. Okay, so the idea is I'll just go into detail. So actually use this one to explain things earlier. Okay, so the thing is this. Okay, for online tracking, what you have is that you have, or especially for discriminative approach, what you have is that you have a sample here, and you have positive example, and then you just sample around, and you put them as negative example. And if you have discriminative approach, then you sample around this guy. If you sample around this region, then it will tell you whether the classifier will tell you that whether the object is likely to be, because the confidence will tell you that. Basically, they will tell you that, and then basically you match that, and then that's how you do tracking, and then you move on to the next one. This is very straightforward. And this is what people call by tracking by detection, because what you do really is you build a detector online, and this is very. I mean, just because I use faces, it doesn't mean that it's only work for faces. It's just one good example for that. All right.
So all this is just one
shot.
object,
Yes.
right?
Yes.
You can track only one object.
Correct. You are right. So yeah, what we do is quite different from you are doing. So basically here we deal with one object and we want to see whether we can track that online and in real time or not. But you are dealing with multiple objects with a lot of occlusion. That's a very different. That's quite different. Yes.
It's a sliding window detector.
No, we don't. You don't do that. You can do that, but it's going to be slow. But for tracking, because you know you can assume most of the time, unless you have ballistic motion, otherwise you can assume that there is a continuity. It moves somewhat smoothly. Of course, if it moves very fast, then the search region will be larger. But for most objects, it moves with certain speed. So you just do detection locally. And there are several ways to do that. You can do exhaustive search locally, or you can just sample. You don't need to use a sliding window with that.
That means in the first frame you know the location.
Yes, here we already assume that in the first frame, because this is online tracking, generic object tracking, so you can have any kind of object, not just faces, cars, all kind of stuff. So we assume that you have some detector. All right, so then so in the next frame you just sample around, and then these two are not the same frame, right? Basically, you know the object location, you sample around, and then the classifier will tell you where it is, and then go on. Okay, so the idea for this work is very simple. Okay, so the idea is this. So basically, from the current object location, you draw samples. Okay, and then you draw positive, negative samples, and then the thing is, conceptually, what you do is that you want to basically, you want to draw kind of filter result, okay? And then basically what is conceptually, okay? I have to stress this, conceptually you are doing dimensionality reduction. Because the feature vectors, the feature vectors are very long. And so you have a lot of features. And so the question is, how do you do dimensionality reduction? If you can project all the long vectors down to some low dimensional space, and then you can easily use a linear classifier to do that. And typically people can use SVM, but here we use a very simple one. You just use naive Bayes classifier to do that, element by element, okay? And that's it. So the question is, how do you do this? How do you compress data? I mean, what I mean is conceptual is because really, this is compressed tracking. So you do not save all the result, and then you do dimensionality reduction. That's what people typically do with PCA and all kind of stuff. But for compressive tracking, basically means that you simply just sample. You simply just extract what you want. You do not save all the vector and then do dimensionality reduction. You do it in one shot. Okay? So the idea is very simple. So there are only two components. How do you represent an object in terms of features? How do you define the classifier? The classifier is very simple. Okay. So if you look at this object here, basically you just want to, it's a 100 by 100 image. So you just need to find some, you need to represent this object in terms of some vector. And you do conceptually you do dimensionality reduction, and you find a linear classifier. That's it. Now, if you look at the hard-like features, I mean, you can also use that to represent an object. What does it do, really? It's nothing but finding edges at different scale, different orientation. That's it, and different position, right? So what they do, well, I don't need to go into detail with this, right? Basically, they try to find some edges, okay? And the thing is, for this work to, at least in the seminar work, what you need to do is that you need to define some basic vocabulary. You need to define, okay, I want to this kind of edges, this kind of edges, this kind of edges, basically x, y direction, and then diagonal direction. Okay, but you need to define this. And how do you know these are good enough? So that's why for some works, they try to define some basic vocabulary. Okay? And so even for small patches like 24 by 24 images, if you define only 4 features, the number of possible features will be 180,000. That's a lot of features. So what do you do? Well, that's why people use boosting to extract useful features. But what you need to do is that you need to spend time to train the boosted classifier, right? And you can do that. But here I'm talking about online tracking. We don't have the luxury to collect all the samples and then train the classifier. Okay, so I'm going to tell you how you can train this in real time. Okay, so another way to look at this is this way. So a few years back, we developed a tracker called MILTracker, multiple instance tracking. So if you look at that, basically, there are several interesting ideas. One interesting idea is that we use generalized hard-like feature. So if you look at, if you look at the feature here, basically all the rectangles will be next to each other. It makes sense because you want to find edges. But in this world, basically what we want to do is that we want to generalize that. So we don't know the basic vocabulary. So what we do is that we extract a few rectangles and we just have a random combination. It's sum up or take difference. So in a way, you can look at this as a relative intensity difference. So in fact, if you look at the literature back in the 90s, there was work done by Pavan Sinha on face detection. So what he did was that for faces, what he did was he manually defined some patches. And you look at difference between different patches. And from that, you can find some threshold. And then you can use a bunch of relative intensity difference among patches and use all of them together to do face detection. It makes sense because for any patch, what is the face? You always find that this part, if you can define the part where this part is usually darker than this part, right? And likewise, this part is, this part, if you compare the difference between this part, usually the difference is small. And if you have enough of that, then you will be able to describe what the object is.
So is it, I mean, what hard is, trying to do hard features, you look at different orientation, different scales and so on.
Right, but for hard feature, the main thing is that there are like edges. Here, this is about relative intensity difference. They are not necessarily edges because they are not next to each other. All I'm saying is that, okay, look at the pattern. You look at the patches and you try to find some stats such that they will tell you, okay, if you look at these two parts, if you look enough example, you can tell the difference.
They're different, they are not
yes.
spatially.
Right, they are not spatially, they are not next to each other. But the problem is this, okay, you can also think this way. There will be even more features. Because here, this one you define a number of vocabulary. here the number of features will be even larger. Okay, so the number of features for this one, what I don't have here. Ooh. Okay. Oh yes, okay. If you look at same pattern, okay, if you use generalized highlight feature, the number of features will be 10 to the 6 to 10 to the 8. That's even larger for the same 24 by 24 pages images. So you gotta have some way to extract features fast, right? And extract important features. And what we find is that, but even though you have a huge set of features for tracking, because what you need to do is to separate foreground from background. For any patch, you separate foreground, tell whether it is a foreground or background, right? So for tracking, we find that with 250 features, it will work pretty well. Now the question is that, okay, among all the features, how do you find the 250, right? And you have to do it fast, okay? And if you look at MILTracker, basically it's nothing but you have feature and classifier. Again, classifier is very simple. Well, sorry, for MILTracker, it's more complicated. We use multiple instance learning for that. But for this particular work, we use very simple classifier. Okay, so if you understand this slide, that's all. That's what compressed tracking is about. So you can think this. Okay, you have this sample. You have this example here. You want to extract some features, and then you want to extract from millions of features. Okay, and such that you want to represent this guy. Okay, so the thing is, so as I mentioned, so here basically if you look at MILTracker with generalized highlight feature, what you do is that for this patch you sum up all the intensity. For each rectangle you sum up with that, right? You sum up all the intensity value, and you can use that. You can use integral image to compute that very efficiently. Now, between patches you can sum them up, or you can take difference with different weights. The weight will, if you use boosting, that will tell you the weight will come from boosting process. If you look at the highlight feature, basically you sum up this and then you take difference. And then how important is the weight, is this feature? You got that from boosting, okay? If you look at this way, then basically you want to represent this up one feature, one particular feature consists of, this feature consists of 4 patches, then that would be, you have some linear combination of this. You have a rectangle, 4 rectangle with some coefficient. And this coefficient will be some number. It can be positive or negative, right? Because this is from the weight that you can get from boosting. If you look at this way, then you can, another way to look at this, okay? So you have this object combined with one particular feature. And so that basically means that you have this image here, you combine with millions of features. And then you want to find the best. You want to find the useful one, and you want to do that in one shot. So that's the main difference. Okay. So basically, what it does is that you can think this way. You have this object. You sample features at different locations, and you sample them randomly, right? Basically, you don't know location, so you sample them randomly and you put them together, and that's why we call it compressed tracking, because you have a. What we do is that we use a random projection matrix. So basically, if you look at this feature, this is only one particular feature that is composed of 4 features. Okay, that basically means that you draw among all the features you have 4 coefficients. Basically, this will be all kind of features that you can have, because here you can combine with all kind of features. And then the coefficient will be on this row. And here, basically what I'm saying is that for this image, you can combine with all kind of rectangular features, many kinds, at any location. And for this particular feature, you just happen to sample 4 of them randomly. Oops. So basically, this will be all the feature set. The same image combined with all the features. And then this will be just one feature that it consists of 4 coefficients. So you can tell that this will be what? Very, very sparse. Because here you have millions of features. This will be a long vector. And then this, the same divergence. So, but here we only have 4. So this will be very, very sparse.
So it's not actually clear. Can you go back? So,
yes.
So you are saying, so you have an image at the top.
You have min match here, and then you combine with one feature, and this will be one particular feature.
So this HK is a filter.
Yes.
Right?
Yes.
So that you apply to particular location, or you apply everywhere?
No, basically we apply this image with all kind of rectangular feature.
Lots
of them. Lots of them. And that's why you build up this column here. So basically you can convert this image with all kind of rectangle at any location, any size. So you have a lot of features.
Okay.
And this particular feature consists of only 4 of them. Because there are many rectangles, right? And here I only use 4. I can use 2, I can use 6, I can use, yeah. So that's why for each row you pick 4. And because this can be,
so these filters are small filters,
yes.
And they're applied at different
anywhere, yes.
And they're like
yes.
hard
yes.
Like that.
I call it generalized hard, yes, yeah.
So you apply lots of filters,
yeah.
thousands of those, and then you're saying you select 4 of them.
This will be one particular feature, but I have more than that because this is like one particular.
Yeah, that's fine.
Yeah.
So you have these communities of 4.
Right.
4 of those.
Right.
And becomes one feature. So the response, rectangle K1, K2, and so on. You
yes.
set up weights, you get one number.
Yes.
And that is one of those features, and you have lots of those.
Yes. So this you can tell. One thing you can tell is that this matrix will be very sparse. It will be.
Is this a randomly generated matrix, or is it?
Yes, it's a random. I'll tell you, it's a random. Yes.
So the filters are hard filters or low hard?
When you took, it's not really hard feature. Okay, it's hard. At best, it's hard like.
Because it is hard, it's high pass, isn't it?
No, it's not hard. It's hard. Again, it's not hard feature. Okay, it's hard like, and then we call it generalized hard like feature. If you look at the original one, then this is called hard like feature. They never call it hard feature. Okay, it's like hard filter, but not the same, right?
So for each rectangle, you insert only one number, or
which one? Sorry.
For each of these, like 4 samples.
Oh, for each rectangle, basically you sum up all the intensity value.
Okay.
Yeah, you sum up, and that's why you use integral image to do that.
And you give a weight to each one.
Yes. So you have to keep weight with that. Yes. And that's why I say if you use boosting, then the weight will be given by boosting process. Because after all, you find out all the you get with 24 by 24 image, you have 180,000 features. And how do you know which one is important? And in fact, for face detection, they find out that the first important one will be here.
So one difference is that hard you have fixed number of
yes.
filters. Right?
Yes.
Here you have lots of them.
Right.
And so you want to be more general.
Right. And then I'm saying that you don't need to go through boosting. I can generate all the features randomly, and it works well.
And so you use all the features and.
No, we only use we select a subset of that because for at the beginning I mentioned that we also the student from Hong Kong he basically follow MILTracker and then with some twist. He start with that. So he use basically the same setup for tracking. Later on you will see that from 10 to the 6 or 10 to the 8 features we only select 250, and that's suffice. Yes.
But that's what boosting is doing, selecting some.
That boosting is one way to go.
Yeah.
Yes.
Good.
So that's it. I mean, so basically, you can tell this is a very sparse metric. And then the number, so basically what happens, okay, as I mentioned, so if you're same one, then basically this metric is very large. And, well, it's very sparse, okay? And typically, we select a fewer than 4 entries on each row, okay? You can use this up to 6, but it doesn't make sense to use more than that. Okay, so basically what happens is that you have, but the number will be, this number will be randomly generated. Okay, here that's a main difference. And so you can think this will be a random matrix, and you combine with a filter, and then you get a filter response. That's it. Okay, so now the question is how do you design this? Okay. All right, so then there are many ways to do that. Okay, so so for tracking, basically we find out that you only typically just need 250. Basically, again, you use the same setup. Okay. So, So you can randomly generate this this matrix, and then there are several ways to do that. The simplest way is this. Okay, you determine a parameter s, and then at each entries you flip a coin, and with 1/2s probability you set it to 1, and because there is a square root of s, so you get a real value, and you can do the same thing for any entries. Okay, and because so you can tell that the most entry will be 0. Okay, because S is small value. All right, S is large value. Sorry. Okay, so then you can generate this matrix, but there are many other ways to do that. Okay, so and then the other thing is that why does it work? So then with detail you can refer to a paper. Basically, there are some works on why this makes sense, why random matrix works well in compressed sensing, and then we use the same ideas to explain why compressed sensing idea works well for tracking. Okay, and then basically the main idea is that okay, if data satisfy certain property, then you can define random matrix very well, and you can reconstruct the signal very well. Okay, that's one idea called RIP. And for random projection, there is another algorithm called Johnson-Lindenstrass lemma. So what happens is that it's like embedding. So you have two endpoints in the high dimensional space. How do you project them to the low dimensional space and preserve that very well? And then basically the lemma says that okay, if you have enough points and it satisfies certain condition, then you can use a random projection to preserve all the energy between two nodes with random projection. I'm not talking about isometric or LLE. But this basically just, with random projection, you can do that very well. And there is some serial. So then there's a link between from the random projection matrix area and then with a link to RIP, which is used in compressed sensing. So so this is not our work. Basically, it just goes to show that okay, the same idea can be applied to this guy here. Okay, and there are many other ways to design this random matrix such that you can have a sparse representation. Okay, I won't go into detail, but and that's it. So basically, the idea is very simple. You just need to design this random projection matrix, and that's all. And after that, conceptually, okay, because you have compressed tracking, right? So basically, with this compressive process, then you select a small set of features. Then you say we use 250 dimensional vector. Then for each dimension, you just use a naive-based classifier to do that. Basically, you have 200 dimensions. Conceptually, you project a vector from high dimensional space to low dimensional space. And then for each dimension, you build a naive basis classifier, and then you just use a scalar Gaussian to tell whether it's a foreground or background. This is mean, and then that's it. Because if you use a scalar to do that, then you can update this Gaussian density very easily. Because this is a closed form. With scalar, you can do that. All right, and that's all. So this just goes to show that okay, if you have positive example and negative example, then you can model that very well with scalar along each dimension, and then you can just cut it. Very easy. And then you have 250 dimensions, so you can put them together. That's it. Okay, so this is summary, and that's all. Yeah. Otherwise, it runs very fast. It runs about 150 frames per second in MATLAB, 3 GHz machine, and the code and data set is available on my website. Just show you some results. Okay, I guess I'll skip some results. Instead of showing some results, I'll show you some recent work on that. And then, of course, we have some quantitative evaluation with success rate and with location error. Okay, so that's the same stuff. Some result. For details, please read the paper. Okay, and okay, so I'll use 5 minutes to describe the most recent work on which tracker works well. Okay, so here I only care about single object online tracking. Okay, I don't care about. Well, we are not concerned with multiple object yet. Okay, and this is done with Yu and Zhang Lin. So basically in this work, basically we want to tell that okay, there are so many trackers. Okay, which one perform well? Okay, so that's the main idea. And then we propose several metrics for that. And okay, so. And from shading, I forgot to put there. So there are a lot of works on performance evaluation, and it's very important. Okay, and there are a lot of standard data set, but in tracking we haven't seen that yet. There are some data set from PASS and Vivid, but there are many for surveillance. Okay, and then for tracking, in recent years there are some more codes. But if you look back 10 years, there were not many codes around, okay, and all data sets for that matter. So
you may have to second them.
yes, okay. So basically the idea is that we want to build a library, code library, and then you can use everything, and then we want to, and later on you just need to click once, and then you can get all the results. Okay, so what we do is that, okay, we compare 30 algorithms. If your algorithm is not here, then please let me know. We haven't found the code yet. Okay, these are 8, and then we compare, okay, these all kind of codes, okay, that we can find. And then obviously, actually this.
So which one was the best?
Okay, I'm telling you.
It's not yours.
I have to cut it off. No. Okay, so we use 50 sequences for that. Okay, so for each algorithm, we evaluate about 500,000 frames. So you can do the math. 500,000 frames times 30 algorithms. And these are, we sort the video in terms of difficulties. And this will be the most difficult one, that most algorithms fail and so on and so forth. We want to extend that to 100 video, but we didn't have time to do that yet. And we put the attribute amount for all the videos. And then I'll quote, these are just to tell you what we mean by terminology. And then you can see that you can look at all the videos. Not all the videos have all the transition factor that we want. And there are 2 metrics. These are 2 standard metrics, but these are not good enough. Okay, so basically instead of that, these are 2 standard metrics. That is what we call by one shot. You basically just run it once, that's it. But the other one is that they usually, if you look at that code very carefully, well, now you don't need to look at very carefully. You will find that all the codes are very sensitive in initialization because these are online tracker. Okay, so basically instead of doing that alone, we perturb all the tracker temporally and spatially. So basically you can initialize objects with some perturbation. Likewise, you can start the tracker at different frame. If you start the tracker at different frame, the result will be different. Okay, and then you just sum them out and take different. Okay, so here are some results. So this is standard what people do. Okay, and for temporal, well, this is what I'm saying. So with one, this is difficult for you to read, but basically the best one that we find so far is probably struct. It works pretty well. It's by filter. Yeah.
That's what we found also.
Okay.
So you evaluated how many trackers? 30 trackers?
30 tracker, 50 sequences, and different ways.
So we did 19 for 300 sequences.
Yeah.
Okay. Yeah, it was amazing. This tracker works good.
Yeah. And then the second one is the one that I just described. It's very simple. The first talk. And then so on and so forth. And then IPT also works pretty well. In some, well, you can look at it. You can slice them in different ways. I can show you all the detail, and then you can read it. But it would be difficult for you to read it here.
So maybe we can stop here because some
yeah.
people may have to go
sure.
to class.
Okay.
And some can stay.
Yep. So that's all I have. You can look at different.
Our paper will be out of business.
No, we can work together.
CVPR.
Yeah. Well, the world is big enough for many of us. You know.
Okay. Okay.
Yeah.
So somebody has to leave, that's fine, you have class. But more questions, please ask questions.
Yeah. No, please.
So for the second method you described, the random matrix, you cannot modify that over the...
Good question. So this is a bit different. Okay, for random matrix, that one we fix the random matrix, but we update the classifier. That's a little bit different. In the previous work, we updated the appearance model. Okay, but here we basically the random matrix once it is designed is fixed.
Yeah, so because otherwise you won't be able to compare them.
Yeah, yeah.
The random matrix is set just one time.
Yes.
And just selects the feature.
Yes. And you just update, but we still have classifier. 250. Let's just say 250 dimensions. You have 250 naive basis classifier. There is a mean for each one of them. You query cut it.
Yeah, like in boosting, you learn which feature is more important, right? And
yeah.
You're just assigning random, right? So what is...
Here, basically, you're trying to find out the most important threshold, basically, right? Yeah, so this is the thing, right? So it's like, okay, that's why it's interesting. Because in pattern recognition, you probably start with PCA. It tells you that in order to do dimensionality reduction, what you do is that you find also normal basis. all right, so that you can have all kind of series. So you can do, and you have to go through optimization to solve that. Okay, that's one thing. The random projection matrix tell you that forget about whatever you have learned. All you have to do is just design a random projection matrix, and if the data satisfies certain criteria, it works well, just as well as that. In fact, if you look at EMA's face recognition work using sparse representation, a while ago, before that, there was work which is rarely cited called random faces. That one also uses random projection matrix for face recognition. You get all the faces. How do you find out? How do you do dimensionality reduction? You don't do PCA. You don't do L1 miniaturization. You just do random projection. And that works was not, well, it was not published in one of premier conferences, so it was not cited frequently. So that's that. It happens all the time. Yes.
Yeah. Have you compared your method with the regular boosting method?
We do. MILBoost is MIL tracking is a boosting method, and in that we also compare with online boosting. We don't compare with batch mode boosting because it's different. Yeah. But we do compare with all kind of online boosting. There are several ones. One is called online boosting, and MILTracker actually is a boosting algorithm too. These are different ways to do boosting.
Okay, yeah, go ahead.
When you were talking about reduction of the dimensionality, you were talking about embedding from local neighbors. Can you explain a little bit?
Oh, I didn't do embedding. I was using that example. I'm saying that, okay, Johnson Lindenstraub lemma says that, okay, if you have points in high dimensional space, and when you want to project them to low dimensional space, okay, so what do you do? How do you preserve the energy? Basically nothing but if you take difference between two points, you want to preserve all the topology between all of them. You want to preserve similar thing, right? You can do that with what? You can do that with multi-dimensional scaling. You can do that with isomap, all kind of stuff, right? But that requires a lot of stuff to do. You have to go through your sub-optimization problem with that. What they are saying is, forget about all those, just do random projection matrix. If the data has certain property, you can do as well as those.
Okay, so yeah, go ahead.
Sometimes, like some research has said that if you compose your matrix discriminatively rather than randomly, for some applications that's better than.
Yes.
But for your application, is it the case that learning it discriminatively is too hard?
Yeah, that's what I'm saying. It already depends on application. Otherwise, if there's only one classifier that it works well, then we're out of business, right? I mean, if SVA is the best one or boosting is the best one, then why do you need to take a pattern recognition courses, right? So I'm saying the same thing. So for different application, for discriminative approach, and it also depends on how you put things together. I mean,
so it's the exact same formulation that you have. What you do is that the W's that you have in your matrix are chosen randomly.
Yes.
But can it be possible to choose them in a discriminative manner, just like your earlier?
It's possible, but it depends on how many features you have and whether you want to do it online or not.
So in terms of online, because there's the time constraint and computational constraint,
yes,
it's better to do random.
In this case, yes. Yeah. I'm just. There could be other way to do that. It's just the way we find out it works well. I'm not saying that that's the only way to do it.
Okay, last question. No.
Yes.
Have you proposed new metrics?
Yes, there are two. Basically, that's what I'm saying, spatially temporally. Okay, you do perturbation on sample. It's like control stuff, right? Basically, you perturb the object spatially and temporally. When I say spatially, it means that, okay, because all the trackers are very sensitive to initialization. So where do you start? If it's off by 1 pixel, it can be quite significant, or 2 pixels. It's just like saying that detection results are not perfect. All right, and then so then whether a tracker is robust if your initialization is off by a few pixels. That's what we call by spatial evaluation, spatial robustness evaluation. And the other thing is that, like I said, so if you look at all the tracking results, you have to look at very, very carefully because sometimes because it's tracking algorithm, it's online tracking. So if the first frame there is some occlusion, some people just discard this one. I start with some frame with clean slate. But some algorithm works well, even it starts with some occluded part. So that's why I'm saying you can. So for long sequence, you can chop it out, and you can stop at a random term. And that also has to do with the rate of appearance change, because at a certain frame there is more appearance change between a few frames than others.
But you have used precision and deviation as two measures to compare the trackers, right?
Right.
But why are you not using like other methods like F-score? Because like F-score
we do. We have those. I mean, basically, it's ROC curve. You can do all kind of stuff. It's all there. It's all. We have all the ROC curve, and then you just whether you want to represent the whole curve or you just want to represent the whole curve with one value. We have everything there. Yeah.
Okay. Thank you very much.
Thank you. Thanks.